All right, let's take a closer look at how we can calculate this tangent line using the idea of a limit. All right, so we've got some very messy looking graphs here. Let me take a second to talk through what you're seeing here on the screen. On the very left, we have a curve in black, and then we have some lines drawn through it. Now, the orange line is connecting this point to this point on the curve. That would be a secant line. The blue line is connecting this point to this point, so that's another secant line. And then the aqua colored, greenish bluish colored line is what would be the tangent to the curve at this point A. So we have a secant line from here to here, another secant line from here to here, and then we have a tangent line depicted. And the values here are the coordinates for the different points along the curve. So this is the point x1, this is the point at x2, and this is the point at A. All right. So what is the tangent line, or what is the slope of the tangent line? It's going to be the limit of this secant line as this point gets closer and closer and closer to this point. And so at x1, we would say f of x1. At x2, we would say f of x2. So in general, we would say the value is f of x, whatever x happens to be. Now the slope of the secant line is f of x minus f of a over x minus a. So that was from the last video. That's the average rate of change from the point A to some other point x. Now if we take the limit as x goes to a, x gets closer and closer to a, that would be the slope of the tangent line. So we're making x infinitesimally close to a. So we're not saying x equals to a. If we say x equals a, then we have f of a minus f of a over a minus a. We have 0 over 0. That's the problem. That's the problem. We get a value of 0 over 0. So the question is not what is the value of this at x equals a. It's what is the limit of this as x approaches a. That's going to be the slope of the tangent line. So we have m tan. M is usually the variable for the slope. So what is the slope of the tangent line? It's this expression right here, this limit. Now the one in the middle is essentially the same picture, except we are defining this point over here in relation to the point A. So here we have A, and then we have x2. Here we have a, and then we have a plus h2. And the reason why we're writing it like this is that when we get to the definition of the slope, it's a little more compact notation for what's happening with the limit. Because what we're saying is we're starting at a, and then we're going over h units to the next point, and then the limit is as h goes to 0. So rather than saying x approaches a, we're saying h goes to 0. H is just the difference between a and this point x, or this point x. I hope that makes sense. These two expressions will get you to the same place, but usually the limit definition of a derivative is written this way, so it's very clear that you are finding the limit as the denominator goes to 0, and the numerator at the same time will also be going to 0. So that's the problem of the derivative in calculus. How do you find the answer, or what does 0 over 0 actually equal? Okay, and then the picture on the right is just a cleaned up version. You don't have the secant lines on it, you just have the function, and then you just have the tangent line, and that's ultimately what we're trying to find. What is the slope of the curve at any particular point? Okay, so I copied this out of the book. These are just the two definitions of a derivative. I tend to prefer this one, but they're both telling you the same thing. They're saying what is the slope of the line, of the secant line, when the 2 points become closer and closer and closer together. All right, so the only way to really learn this is to see it in an example, and in practice, that's what you have to do. You have to take a type of a function and work out what this limit is to find out what does 0 over 0 actually equal. So what we're going to do here is take a particular case, f of x is equal to x squared, at the value x equals 3. And you could do that. Now, let me just pause for a second. You won't have to go through these steps for every derivative. What we will do is establish rules for the type of function, and then once you know the rules, you can just apply the rules. You won't have to go through this every time. But it is good to see how the process actually works for finding the derivative through the limit. Okay, so x squared is the function, and we're going to look at the value x equals 3. All right, so we have limit h going to 0. That is always going to be the case. H is in the denominator. And then in the top, we have the value of the function at the point x equals 3. And we're adding h units over from it. And then we're subtracting the value of the function at x equals 3. So that's the setup. Then we insert the function. So our function is x squared. And so the argument is 3 plus h. That means it's 3 plus h squared. And then what is f of 3? Plug in 3 in for x. 3 squared is 9, so it's minus 9. So this is what we're taking the limit of. 3 plus h quantity squared minus 9 divide by h. So next step will be to expand out this, this squared function. And we get 9 plus 6h plus h squared minus 9. Notice the 9's will cancel. And then you have 6h plus h squared divide by h. Okay. So going to the next line, we can factor out. So remember, the 9's are gone. We can factor out the h's. So you have h times 6 plus h divide by h. And here you might notice we can just cancel out the h's, right? So there's an h here, an h here. Those can cancel, and we just have 6 plus h. Now we arrive at a function where we can plug in the value at the limit, right? So the limit is h going to 0. If h goes to 0, the limit of this function is just 6. And so we see that the slope of the tangent line of this function at x equals 3 is equal to 6. Okay? So that's the process to find the slope of the tangent line. If you want to find the full line, like what's the equation of the line, now you need to know another point. So we know one point on the line is at x equals 3, and f of x is going to be equal to 9. So the point 39 is on the line. And now we know it has a slope of 6. So what we're doing right here is working out where is the y-intercept going to be. So we know it's going to be a function that looks like y equals 6x plus b. 6 is the slope. We know that when x is equal to 3, y is equal to 9, so we can plug those in. Solve for b, you get b is minus 9. And so the whole equation for the line is 6x minus 9. Okay, so this is one in detail example of finding the derivative, or finding this, I'll say for now, just call it the tangent line to the curve. You'll see that that's actually the derivative. But finding the tangent line to the curve at x equals 3. Okay, let's take another example, and I'll go through this quickly, but if you need to, you can always pause the video, come back, try these on your own. There will be some examples to try in the practice problems as well. As I mentioned, we will use derivative rules most often to calculate derivatives and slopes of tangent lines. but it is good to go through this process so you really understand what is entailed. So function is 1 over x in this case, and it's at the value x equals 2. So we plug into the formula. Now this time, just to show that it works both ways, I'm going to use the other formula for the limit definition of a derivative. Instead of h going to 0, we're having x go to 2. And so instead of h in the bottom, it's x minus 2. But then in the top, we have f of x minus f of 2, so 1 over x minus 1 over 2. We just plugged in the function and used this point. Okay. So now we have this function here, and to simplify it, we can use a little trick. Multiply by 2x over 2x, which is effectively multiplying by 1, and you can always multiply anything by 1 without changing it. If you multiply 2x through on the top, you get 2 minus x, and then on the bottom, you have x minus 2 times 2x. Now, why this trick will help us is because 2 minus x divided by x minus 2 is really just negative 1, right? 2 minus x divided by x minus 2 is negative 1. And so we have negative 1 over 2x, and here we're at a place where we can just plug in 2 for x, and you have minus 1 over 4. That's our slope, minus 1 over 4. Now, if you're wondering why didn't we just plug in the 2 earlier, at any of the previous stages, if you plugged in the 2, you were going to get 0 over 0. And the name of the game is to start here and keep going, simplifying, until you get to a place where you can plug this in and it's not 0 over 0. Because 0 over 0 we don't know what to do with. So if I plugged in x equals 2 here, I'd have 2 minus 2, 0. 2 minus 2, 0. 0 over 0. That's the problem. But after simplifying, right, you get this function here. And so essentially what we've done here is this function and this function are almost the same. We've just removed a whole from the function to calculate its limit. And we find a limit of minus 1 over 4, so that is the slope of this function at this point. All right, so the graphs here on this slide show you both of those functions for which we've just found the tangent line. The first one was x squared at the value x equals 3, and we found a line y equals 6x minus 9 is the tangent line to the curve. So it shows both of those, the original function and its tangent line plotted. Same thing over here with the other example, f of x is 1 over x. And if you work out the full equation for the line, you'd get, remember, it was a slope of minus 1 over 4. And then to make the tangent line go up to touch the curve, you add 1. And so we have the tangent line just touching the curve here at that point, x equals 2. So that's just visually showing you we've calculated the tangent line to these curves. Now lastly, I'll point out that this process that we've just gone through to find the tangent line to the curve is also called linearization. And in addition to being the basis for a derivative, this is a pretty common approximation method. So using a derivative is a common approximation method to a curve by taking what is some more complicated function and replacing it with a line at that particular point. And what I'll say to you is, without knowing it, you've used this quite a lot in any class where you've had formulas. Because oftentimes those formulas are really just the linearizations of something more complicated. One that comes to mind for me is springs. When I teach physics, we have Hooke's law for springs, and it's a linear equation. It says that the force that a spring applies is directly proportional to how much you stretch the spring. So you stretch the spring, it pulls back. And that's a linear function. It's a linearization of something that's actually more complicated. So if you were to stretch a spring too far, it would stop being linear. So if you were to actually calculate what is the force um, in relation to the amount the spring is stretched, it wouldn't be a perfect straight line from 0 to whatever the maximum is. It would be some type of a curve that is flat over a range of amounts that can be stretched. And so that's what we would call the linearization. And that is quite common that in whole, uh, the relationship between two variables is some complex function. Maybe it's an x cubed, or maybe it's a logarithm, or it's an exponential. But if you restrict to a small domain, you can approximate that curve with a straight line. And we do that often in all areas of science and medicine, sports and economics, and all of the areas that use mathematical modeling. So that's finding the tangent line to a curve, which allows us to linearize and also interpret the rate of change instantaneously along a curve. In the next video, we'll start to look at some derivative rules so we don't have to go through the process of finding the limit of every function at every point whenever we want to know what the slope of that tangent line actually is.